Okay. All right, so let's begin. Good morning or good afternoon, everyone, wherever you are. Today we'll do a presentation about the geothermal research we do in Canada for INRS team. INRS is a graduate student university that does research. At INRS, we only have master and PhD program, no undergraduate degree. But we do a lot of research. So we're sort of a hybrid in between a research center and a conventional university. Let's say we're a university, but with a different model. And we do a lot of research on, well, geothermal energy in my group, from shallow geothermal energy on shallow resource and system, including ground-coupled heat pumps, borehole thermal energy storage, to deep geothermal resources associate sometimes with power generation or heat production. Our research is quite diverse. We work in different environment in Canada. For example, looking at the geothermal potential of flooded mines, and we'll have a presentation on this. We also do work with remote community. Actually, a lot of our work that we will present today, it's with the northern remote community that are diesel dependent and need a solution to offset diesel. So we'll have presentation on well, borehole thermal energy storage and how it could be well, implemented in remote community facing permafrost challenges. Also, we'll look with another presentation at the ground coupled heat pump system and how it could be tied with hybrid heating system, and a last presentation about deep geothermal resources, also for the South Slave region in Northwest Territory. So looking at the North also. So the idea for today, we have 4 presentations. Each of those presentations will be made by a student at INRS or group of students. The idea is to do 10-minute presentation for each project, and then we'll move into questions at the end. So our first presentation is by Samuel and Mariana. Samuel and Mariana are both master students at INRS, and they have been working on the geothermal potential of flooded open pit mines in southern Quebec. So Samuel, Mariana, please share your slide and start the presentation.
Okay, thank you.
Thanks. Okay. Yeah. Thank you. Okay, so hello everyone. Thank you for attending our session. Mariana and I are both master students at the INRS located in Quebec, in Canada. Our project focuses on the evaluations of the geothermal potential of abandoned and flooded open pit mines, considering the available thermal resource and geochemical aspects. Oh, okay. So the geothermal potential of abandoned underground mines is well known for their great potential of heat extraction. But on the other hand, the geothermal potential of abandoned open pit mine is often overlooked. But with the large volume of water available, maintained at low temperature, they have also great potential, but now for cooling applications. So in our presentation, we will discuss about the estimations of available thermal energy resource in open pit mines, and it will be followed by Mariana's project with geochemical and physical-chemical considerations of the water. Our study site is located in Thetford Mines in the southern of the province of Quebec. So Thetford is a city well known in the region for its past mining activities associated with asbestos extraction. And now the territory is shaped by abandoned and flooded open pit and underground mines. So because the population is growing around these sites, that makes the geothermal resource more accessible and interesting for residential and industrial sectors. So let's begin with my research project. So I will explain to you how I estimate the available geothermal resources in fluided open pit mines. The thermal energy contained into a body of water can usually be evaluated with a volume method, which is consider the volume available, the thermal properties, and the difference temperature between the initial and final temperature after an exploitation. In my study, I will present the result by the thermal power, which is represented by the energy divided by an operation time, which will be 25 years in my case. And this energy will be deducted by the thermal power absorbed by the compressor of the geothermal heat pump. So the processes considered into my thermal balance is the energy that can provide the available volume of water, the contribution of the rainfall, groundwater, runoff, and surrounding rock. And I will show you the method that I use to determine the volume and the initial temperature of the water contained into the open pit and for water supply. And I will show you the method for volume, temperature, and thermal properties of the surrounding rock. So the volume of the water contained into the open pit is evaluated with a bathymetric survey conducted using a Garmin EcoMap sonar, which allowed me to determine a water volume of 23 million cubic meter. And the initial temperature of this water is evaluated with a continuous temperature profile of the water throughout the year, using a buoy system and temperature sensors. So the average annual pit water temperature is evaluated around 5.25 degrees Celsius. The volume of the water supply is evaluated with an hydrogeological balance with the third weight method. So I assume that all precipitation that falls into the mine's watershed will enter into the mine water by direct rainfall, surface runoff, and groundwater flow. So the initial temperature of the rainfall and the runoff is considered to be equivalent to the ambient temperature, and the initial temperature of the groundwater is considered to be constant during the year, which will be represented by the undisturbed ground temperature. So the volume and the temperature of the surrounding rock are more difficult parameters to determine. So to do this, I use this formula, which is characterize the heat transfer by conduction in a solid in a one-dimensional semi-infinite domain in transient state. So the principle is to evaluate the propagation of a temperature in a solid in time if there is a sudden change in the temperature condition imposed at its surface. So to apply this principle to characterize the heat transfer from water to rock, the distance of the propagation of the temperature must be determined for each axe of the open pit, because the initial temperature will act as a boundary condition and will vary in function of the spatial component of the geometry. So the maximum distance of the extent of the propagation of the temperature is established when the temperature difference between the calculated distance temperature and the initial temperature is equal to 0. Oh, not yet. Thank you. And I assume to represent the open pit, I assume a simplification of the geometry using a half ellipsoid form. Okay, no, thanks. So the thermal properties of the surrounding rock is evaluated with a rock sampling in the field and a laboratory analysis with a thermal conductivity scanner. And with 20 rock samples collected around the pit, I evaluated an average thermal diffusivity around 1.4 minus 6 square meter per second and an average volumetric heat capacity around 2.7 megajoule per cubic meter per Kelvin. So finally, the available thermal power for cooling, if I assume a final temperature of 25 degrees Celsius and an operating time of 25 years, I can estimate a resource around 6 megawatt. And if I consider the energy consumed by the compressor of the geothermal heat pump, I can evaluate the thermal power available for buildings could be around 4.84 megawatt. So this is the end for my part. I will hand over to Mariana.
Thank you. Now I would like to go through the geochemical profiling of Carey Canadian open pit. But first of all, why is geochemistry important? The open loop heat pump systems are designed to pump water from the pit and it will flow into the system. And this water has its own physical chemical properties. From literature of several heat pump systems, applications in groundwater studies has shown significant mineral precipitations in due to mixing different redox conditions, causing pipes clogging within days or even hours. Moreover, the injection would also create heat plumes that will also rise the temperature of water. So that has raised two hypotheses to us. First is, if we induce mixing, would that cause different mixing of redox conditions in different water columns, different depths? And would that cause mineral precipitation and clog the pipes? And if so, rising water temperature would have thermal effects on biogeochemical reactions. These pictures that I'm showing are from the buoy system installed that Samuel showed earlier. The temperature sensors were arranged in the alloy cables, metallic alloy cables. And when we went to retrieve them twice in 2022, they all showed mineral precipitations all over the cables. So therefore, to understand the environment is important for a better system design and for its sustainability. Considering the dynamics of the water from the peat lakes are similar to natural lakes, we have decided to do seasonal sampling during autumn, summer, spring, and winter. We have sampling two profiles, one deeper and one shallower. And we sample major cations, anions, dissolved inorganic carbon, dissolved organic carbon, isotopes of water, stable isotopes of water, and physicochemical parameters. And based on preliminary results, we can already discuss some limnological dynamics and hydrogeochemical phases of the water column. By analyzing the temperature profiles, the thermocline was defined where the delta T is maximum, and the hypoleminion, there is a upper and turbulent zone in the upper boundary is in contact with the atmosphere, and the lower boundary is in contact with the metaleminion, which is a zone with a higher gradient of temperature. And finally, under the thermocline, we have the hypoleminion. These layers, they are contained in a major layer called the mixoleminion. This major layer goes through overturning twice a year, once during autumn and another during spring. This means that the surface water sinks when it reaches 3.98 degrees Celsius, uplifting deeper waters before establishing the summer and winter certification. These overturning periods are important because they bring oxygen to deeper waters. So in the next graphs, we can see that in the mixoleminion, we have a greater variation of isotopic signal compared to the monoleminion, which is a layer that is high in salinity, that is defined under the chemocline, and it shows higher density and anox conditions. And this water shows, the water from Carry Canadian shows good quality, and it's a magnesium calcium sulfate water type. And we chosen this stiff graph to show you how the concentrations of major cations and anions are constant in the upper layer, and they rise in the bottom layer. So finally, what we can understand so far in the geothermal aspects is that the open pit mines have great potential for cooling applications, and that the thermal balance should consider the energy contribution of water supply and surrounding rock. And in geochemical aspects is that field observations, they correspond to what we found in the physicochemical profiling. And we found two main layers with different redox conditions. So the next steps for both projects will be modeling. For geothermal, we model the thermal short circuiting effect to minimize this effect. And for geochemistry, we will model increasing temperature and mixing different redox conditions to see what we change in the main reactions. That's it. Thank you very much.
All right, thank you, Mariana and Samuel. I think we'll move to the next presentation. Abra, can you share your slide? Really interesting research you guys show, with great potential for cooling, right? We're using those open pit water. So Abra is going to present about solution to minimize permafrost under borehole thermal energy storage. Abra is a student at Reykjavik University, and she came to INRS to conduct her research project that still has links to low temperature geothermal heat pump system, but has been conducted for remote northern community. So please go, Abra.
Okay, so thank you for the introduction, Jasmine. My research is on minimizing permafrost thaw and maximizing heat storage in Baker Lake, Nunavut. Again, my name is Abergold. I'm from University of Reykjavik, Iceland, but I'm working in conjunction with INRS, Jasmine, and Mafalda. And my advisor in Iceland is Einar. So first, I'd like to talk about Baker Lake's unique setting and community. Baker Lake has a mean annual ground temperature of -7 degrees Celsius year-round. It's in a location of continuous permafrost, meaning the permafrost doesn't thaw for at least 2 years consecutively, but the permafrost in Baker Lake has been frozen for much longer. It's located in mainland Nunavut, as shown here just by this figure, and the climate is considered subarctic. The community is a population of 2,061 Nunavummiut as of 2021, and the community is almost entirely reliant on diesel fuel, which is extremely risky because transportation and storage sometimes leads to oil spills, and diesel fuel is becoming increasingly more expensive as time goes on. So just an introduction to BTES systems. Borehole thermal energy storage, or BTES systems, store heat seasonally in the subsurface using borehole heat exchangers, or BHEs, which is pictured in the figure on the left. This is a BHE storing heat in the summer, leftmost figure, and extracting heat in the winter. Basically, the flow just changes direction. Oh, excuse me. And BHEs essentially carry waste heat in the summer from diesel gensets via transport fluid. And in the winter, they use the same transport fluid at a different temperature to extract this heat from the subsurface. So when BTES systems are installed in permafrost regions, 3 scenarios can occur. So the BTES system in scenario A can heat the sediments to a point where there's a cold contact and a warm contact. And at that cold and warm contact, there can be slip, which could damage the system. The sediments could heat around the BTES system, causing compaction, which can damage the system. And if the permafrost thaws, then you can get convective heat transport settings instead of conductive, which is better for storing heat. And so the objectives of this project are to develop a BHE and BTES model to evaluate permafrost mitigation solutions in a program called FEFLOW. We determined which permafrost mitigation solutions deter the thaw of permafrost while maximizing energy storage. We created a report deliverable to CanMet Energy Ottawa, and we met the thesis requirements from Reykjavik University. Our hypothesis was that using permafrost thaw mitigation strategies, it may be possible to overcome engineering challenges related to permafrost when storing energy in the subsurface. And our research question was, what is the most efficient way to maximize energy storage while minimizing permafrost thaw with this technology? The single BHE model was developed to test grouts and pipes, vacuum insulated tubing, or VIT, in the upper borehole section, air in the upper borehole section, and thermosiphons. The upper borehole section extends from 4 to 20 meters, depending on the scenario. And we tested these scenarios to find a solution to privilege to recommend. The model also simulates the latent heat effect from freezing and thawing of permafrost, seasonal ground temperature changes, adiabatic model boundaries, negligible fluid flow, and it simulates heat transfer boundaries between other BHEs and a central BHE in the middle of a borehole field. On the right is just the schematic of air insulation, which extends from 4 meters to 20 meters in some scenarios. And this is the heat exchange that I was talking about. So at any point between 2 BHEs in the middle of the field, there's going to be no heat transfer because the BHEs are both pushing out an equivalent amount of heat at that location. So we are saying that this BHE that we've modeled is in the center of a field surrounded by 6 other BHEs that are not modeled just in the single borehole model. The BTES model, we've simulated 100 BHEs to test insulating only the outer ring of the field with air to see how that affects the propagation of heat laterally from the field. We've insulated every borehole in the field with air, and we've also taken no action in our scenarios. The model also simulates seasonal ground temperature changes and negligible fluid flow. The latent heat effect is not applied to this model because the computational demands were too high. And so here's our single borehole model results. What we found was that the thermosiphon wasn't as effective as air insulation or VIT in summer. And this is just a graph showing the ground temperature around the borehole about 0.23 meters away from that central borehole. And as you can see in the injection season or the summer season, when the ground temperature is the warmest, the air insulation and VIT kept the ground cooler than the thermosiphon did, but not cold enough as to reflect the natural gradient that the permafrost shows seasonally, which is demonstrated by the black curve. And we also found that in the winter, if you look over on the right side of this figure, the thermosiphon was capable of keeping the ground cooler than the air insulation and VIT, but still did not meet that general curve of the natural ground temperature. We also found that a combination of solutions, thermosiphon and VIT, which is represented by that purple curve, was the most effective and also the most expensive. So our solution to privilege was air insulation because it essentially was cost effective since it wouldn't cost anything to not grout the borehole. We also found that extending air insulation to 16 meters depth was more effective than just leaving the air insulation at only 4 meters depth in the model. So as you can see by this orange curve here, at 4 meters depth, the temperature is much less dramatic, the temperature changes, than the air insulation at 4 meters depth that only extended to 4 meters in the model. And this is just showing that the changes to power injected or extracted in the model were negligible between scenarios. And this is the BTS field model results. So it turns out that insulating every BHE in the field, just on the outside of the field, I mean, at the outer edge of the BHE, that's what this graph is for, it's ground temperatures. Insulating every BHE is much more effective than insulating the outer BHEs just along the edge of the field, or not taking any action at all when it comes to preventing the ground from warming any more than it would naturally. And then the power injected and extracted was once again showing negligible differences between scenarios in this model. So we concluded that changing grout doesn't have an effective impact on the temperature and the overburden. We also concluded that 16 meters of air insulation improves the effectiveness of the air insulation solution. Thermosiphons were less effective in summer. Air insulation is a solution to privilege in this environment because the cost is expected negligible. And if there is material contact between boundaries, heat's going to transfer. We found the thermal conductivity is the greatest factor in determining how much the ground temperature increases. And we also found that insulating every borehole is slightly more effective than the BTES field at large. And that's the end of my presentation. Thank you very much for listening.
Thank you, Abra. Maybe while I talk a little bit to the transition, if you can, well, just quit the slide, and David, maybe you can pull up your slide. Abra, that was a really nice presentation, I guess, on a very Canadian specific problem or a problem that affects, right, communities that live in the high north and face permafrost, right, and would like to develop geothermal energy and permafrost. Next presentation is by David. David is an INRS student who is from Colombia and came to Quebec to actually look at the technico-economic analysis of a geothermal heat pump system that could be combined with other type of heating system like biomass and solar to heat buildings of remote communities. So now we're still on the northern topic, looking at communities of Nunavik. Please go, David.
Okay, hello everyone. Okay, my name is David Moreno. I'm a master's student in air science at INRS. and I'm going to present my research project, which is called Techno-Economic Analysis of Geothermal Biomass, Techno-Economic Analysis of Geothermal Biomass and Solar Hybrid Heating System for a research station in subarctic climate. My research director is Jasmin Remond, and my research co-director is Luis Gosselin from Laval University. Okay, so to put you a little bit in context, the study area of my project is in Nunavik, which is located on the northernmost part of the province of Quebec. This region is characterized because it has a very low population. It has a very limited energy infrastructure and energy transportation infrastructure. It has a very extreme weather climate, and it for all of these reasons, depends mainly in diesel for all the heating needs and electricity needs. This region is not connected to the national grid, so that leads to a very high cost of energy. Recently, like there were conducted several studies to try to improve the energy independency of this area, of these regions. And they were evaluated like biomass alternative, solar energy, geothermal energy. However, in several occasions, these alternatives are evaluated under different methodologies and under different process. So, and this make it difficult to identify maybe an optimal alternative of mix of alternative that could lead a better hidden system for these regions. So the idea with my project is to evaluate different hidden system alternative for a new research station that will be built in Umuyaq using a life cycle cost analysis. This life cycle cost analysis is a tool that allow to evaluate like different costs that incur in a lifetime period. So for example, not only the equipment cost, but for example, environmental cost or maintenance cost or all of this. So the alternative that I'm evaluating in my project is if the biomass alternative with a wood pellet furnace, solar energy with solar PV, and geothermal heat pumps, and a conventional heating system, which is a diesel oil furnace. So to do the part of the evaluation for the geothermal system, it is very important like to have like the thermal properties and physical properties of the ground where the building will be built. So I perform a field work and a laboratory work where I went to Umuyaq, and I took 24 samples of quaternary deposits and 8 samples of rocks, and these samples were taken and are characteristic from the study area of where the building will be built. And where an important thing to say is that in the area where the building will be built, there's 7 meters of quaternary deposits before reaching the basalt. And here I have like some of the values of the thermal conductivity and thermal diffusivity measured in the INRS laboratory. So for example, for the rock, for basalt, I have an average thermal conductivity of 3.49 watts per metric Kelvin. For marine sediments, 1.57, and for fluvioglacial sediments, 1.31. So then when I have like the thermal properties of the study area, now I perform a building energy simulation with a transit software. This software allow me to know like the heating needs of my building. The building, just to put it a little bit in context, the building that I simulate in transit, it has 2 floors. Yeah, the first floor, it is the mechanical room. It's a mechanical floor and a storage room. So there were no people. There won't be people living like here. And the second floor is the place where the people will live or will stay. So the first floor has an area of 207 square meters, the second floor 222 square meters, and it has a different heating set points, temperature set points, because of the reason that I explained. Like the first floor only 15 degrees Celsius because it's the storage room, the mechanical room, and the second floor where the people live like 20 degrees Celsius. Another important information is that this building will have a foundation piles. So the geothermal alternative will be mixed with this foundation pile. So at the end, we will have like an energy pile. Other important information is that as this building is a research station, not all the year will be occupied at 100% of the occupants. Like in the colder months, it has a 50% of the occupancy, and in the warmer months, it has the 100% of the occupancy. So at the end, the results of the annual space heating needs for each floor, it has 56.8 for the first floor, kilowatts hour square meters, and for the second floor, 217 kilowatts hour per square meter. Here, it's important to say that the difference between the heating needs between the first floor and second floor, it's because as you can see in the image, like the first floor doesn't have like many windows. It only have one door that is exposed to the exterior. So this floor it won't have like very big loss temperature loss. But in the second floor, it has a lot of like windows and all of that. So that's why there are a big difference on the annual space heating between the two floors. This is the peak load per floor, and it was used to size the system. So here we have like the scenario simulated. It was 4 scenarios. You can see it here. Scenario 1, which is business as usual. So I have like, for example, and in the columns, we have the heating system. So for example, in the business as usual, it's commonly that in the northern Quebec, in Nunavik, the heating needs is covered by the fuel oil furnace. So in scenario 2, we have like that the heating needs is covered by the wood pellet furnace, and scenario 3 and scenario 4 were the alternatives where we mix the heating system. So for example, in scenario 3 we have that in the first floor, the heating needs of the first floor are covered by the geothermal source heat pump. In this configuration, I have like a 5 borehole heat exchanger of 50 meters each borehole heat exchanger to have a total of 250 meters of the total length of the borehole heat exchangers. And the electricity needs to run this alternative, to run the geothermal heat pump, it's covered 100% by the solar PV system. And in the second floor for this scenario 3 is covered by the wood pellet furnace. And for the scenario 4, we have the first floor is covered, the heating needs of the first floor is covered by wood pellet furnace, and the second floor, the heating needs of the second floor is covered by 30% for wood pellet furnace and 60% for the ground source heat pump. And in this case, the configuration is 8 borehole heat exchanger to 50 meters each borehole heat exchanger to have a total of 400 meters. Also here, the electricity needs to run the heat pump. It's covered by a solar panel, solar PV. So the net present cost and the levelized cost of energy were chosen to evaluate the economics part of these different scenarios and to compare these scenarios. So it's important to say that the analysis period was 50 years of life cycle cost analysis, and that the total cost needed to estimate the net present cost, it is the sum of capital cost, annual cost, and periodic cost. Here I have like each of the costs incurred and considered in my analysis. Like for example, in capital cost, we have the equipment cost, like the furnaces, the drilling for the borehole heat exchangers, the PV panels, and also the storage system for the PV panels. Also, we have like the installation and labor, the shipping cost. For the annual costs, one of the costs very important, like obviously is the energy cost, like the pellets cost or the diesel cost for each alternative, and also we consider a diesel spill risk cost. As Abra said in her presentation, like it's pretty common that they are like diesel spills in Nunavik, small diesel spills sometimes, but with the time it getting big amounts of diesel spills, and the cost for soil remediation, it's very high. So it's very important to take into account this in the economic analysis. So we establish a diesel spill risk cost. And for periodic costs, yes, like equipment to be replaced because it's a 50 years analysis period and all of that. So at the end, here I have like some of the results. Like here in the first graph, we have an annual greenhouse gases emission of tons of CO2 equivalent. So the scenario one, which is only covered, the heating needs is covered by diesel furnace. Well, it has the biggest one, and scenario two, it's only for the wood pellets boiler covering the heating needs, and it's getting lower because, for example, in scenario 3 and 4, it's the mix of geothermal energy and biomass energy, which it has a very low like emission of CO2 equivalent. In the final like LCOE analysis, we have that the scenario 1, which is the business as usual, has a value of $0.31 per kilowatt hour. The scenario 2, 0.26. Remember that scenario 2 is only heating needs covered by a wood pellet furnace. So it presents the lower LCOE. However, remember that it's important to remember that there's no production of wood pellets in northern Quebec, so all the wood pellets needs to be imported from South Quebec, and this represent that. I mean, this alternative doesn't improve the energy independency of the region, which is one of the objectives that we want to fulfill. So even if the more economically important, well, it doesn't improve the energy independency. So for scenario 3 and scenario 4, which is the geothermal system with the biomass system and solar PV, we have a higher LCOE. However, are the options more that improve more the energy independency of the region. In this case, I consider that the scenario 4 is the scenario that represents the best trade-off alternative for showed overall good energy independency, low greenhouse gas emissions, and competitive LCOE. So yes, that's all. Thank you.
All right, thank you, David. Maybe it's time to well, stop sharing your screen, and Mira, you can share your screen, and we'll move to next presentation. Really interesting presentation, David, that shows the power of hybrid system to make a heating system more economic. Notre prochaine présentation sera effectuée en français par Mira, qui est une chercheure postdoctorale à l'INRS. Et maintenant, on va regarder un peu plus les ressources géothermiques profondes, mais toujours pour les communautés nordiques isolées, cette fois-ci des territoires du Nord-Ouest. Alors, Mira, à toi la parole.
Alors, bonjour tout le monde. Oui, merci professeur Jasmin de l'introduction. Moi, c'est Mira, alors je suis postdoc à l'INRS avec l'équipe de professeur Jasmin et ce projet est aussi en collaboration avec le Northwest Geological Survey qui est représenté par Victor Tirlaki. Alors, ce projet porte sur l'évaluation du potentiel géothermique profond dans la région au sud-ouest des Grands Lacs des Esclaves. Alors, cette région, alors, délimitée ici sur la carte en bleu, se situe dans l'extension de l'ouest, dans le bassin sédimentaire ouest canadien. Et les communautés, comme dans la plupart des communautés du nord du Canada, dépendent fortement de l'énergie fossile pour le chauffage des bâtiments. Et cela a un impact important pour l'émission de carbone. Et dans le but donc, de diminuer cette dépendance en énergie fossile, la géothermie est proposée comme une énergie alternative pour remplacer ces énergies fossiles. Et comme montré ici sur la carte, le potentiel serait élevé, moyennement élevé, car le flux de chaleur mesuré à la surface serait de l'ordre de 90 milliwatts par mètre carré, ce qui est le plus élevé dans tout le bassin sédimentaire ouest canadien. Et aussi que cette région a fait l'objet d'explorations pétrolières et gazières. Donc, on bénéficie de ces forages pétroliers pour aider à évaluer le potentiel géothermal. Alors, les principaux objectifs de notre travail étaient donc d'évaluer les propriétés thermophysiques des carottes échantillonnées, y compris la conductivité, la diffusivité et la capacité thermique. Aussi d'évaluer les propriétés hydrauliques, ainsi que la composition minéralogique et les concentrations en éléments radiogéniques qui contribuent à la production de chaleur interne. Et cela permettra donc de mieux estimer la température en fonction de la variation de la température en profondeur, et aussi donc d'évaluer le potentiel du système géothermal. Et toutes ces informations-là permettront de mieux informer sur les décisions futures par rapport à tous les projets d'exploration ou d'exploitation en matière de besoins énergétiques dans ces communautés. Alors, du point de vue, donc, comme contexte géologique de la région étudiée, ici on a la carte géologique montrant les principales formations et avec les principales communautés concernées qui comprend Fort Providence, Kakisa, Fair River et Enterprise. On a aussi les principales failles qui regroupent les formations. Puis ici, on a les localisations des forages qui ont pu être échantillonnés. Alors, avec les deux coupes ici, le socle précambrien se trouve à de faibles profondeurs car la couverture sédimentaire est de faible épaisseur, allant de 1 km à moins de 500 mètres. Alors, avec ce contexte géologique-là, on peut déjà guider le mode d'extraction de la chaleur dans un tel contexte géologique. Comme travaux de laboratoire qu'on a effectués ici à l'INRS, dans le laboratoire ouvert de géothermie, on a utilisé le scanner optique pour mesurer les propriétés thermales, puis aussi avec le compteur du flux de chaleur, on a mesuré la conductivité thermique en fonction de la variation de la température. Puis avec le porosimètre perméamètre, on a mesuré la porosité et la perméabilité. Puis des analyses géochimiques, d'abord à l'INRS pour la mesure des concentrations en uranium, thorium et potassium avec la méthode spectrométrique, puis dans un laboratoire externe pour la composition minéralogique avec la méthode de diffraction au rayon X. Au total, on a pu analyser 84 échantillons de carottes fondues qui couvrent 8 formations et qui proviennent de 33 puits. Alors, directement, comme principaux résultats qu'on a obtenus, on a des colonnes stratigraphiques au niveau de chacune des communautés. Et ces colonnes stratigraphiques synthétiques ont été élaborées à partir des données de forage les plus rapprochées de chacune de ces communautés. Et ici, on a aussi les valeurs de conductivité correspondant à chacune des lithologies qui forment la stratigraphie. Ici, vous voyez nos mesures en trait continu noir, mais qui malheureusement n'a pas pu couvrir toutes les lithologies de la stratigraphie. Donc, nos mesures de conductivité ont été complétées avec les mesures de conductivité de la littérature. Vous voyez ici en trait discontinu. Et aussi, ces valeurs ont été comparées avec les mesures de conductivité calculées à partir des équations empiriques. Alors, comme valeur de conductivité, les échantillons sont plutôt des roches intermédiaires à conducteurs de la chaleur et en termes de perméabilité, ce sont des roches imperméables à peu perméables. On est donc en présence d'un système pétrothermal, d'abord où le transfert de chaleur se fait par conduction et aussi dans un système de transitoire où le transfert de chaleur se fait par convection forcée. Et avec les données de perméabilité et de porosité, on est toujours, qui sont basses, on est toujours dans un domaine pétrothermal, mais où donc la méthode d'extraction qui sera développée sera les IGS ou les systèmes géothermiques élaborés. Alors, pour conclure donc, nos travaux, on a pu effectuer une première évaluation des propriétés thermiques, y compris la conductivité thermique des roches échantillonnées dans le sédimentaire dans la région, puis que ces roches-là ont plutôt une propriété conductrice de la chaleur et que la conduction et la convection forcée sont les mécanismes de transfert de chaleur dominants. Et dû au fait que le socle précambrien se trouve à une faible profondeur, les méthodes d'extraction de la chaleur seraient donc les échangeurs de chaleur et les IGS. Comme travaux futurs qu'on est en train de poursuivre, actuellement, c'est donc d'utiliser les températures de fond de puits corrigées avec les effets du paléoclimat afin de calculer le flux de chaleur et le gradient géothermique et aussi élaborer un modèle 1D de la distribution de la température en fonction de la profondeur au niveau de chacune des communautés concernées. Alors voilà, ce sont nos partenaires financiers qu'on aimerait remercier, puis au robot pour nous avoir permis d'accéder aux données de forage. Je vous remercie pour votre attention. Thank you everyone for your attention. please feel free for your questions. Thank you.
Merci Mira pour la présentation. Il nous reste à peu près une dizaine de minutes pour prendre des questions. So we have about 10 more minutes to take questions. We could also extend a little bit if needed. So I'd like to, well, open the door, the microphone to the floor, and people that have been listening to the presentation, do you have questions for our presenters? Est-ce qu'il y en a qui ont des questions? Et n'hésitez pas à poser vos questions en français, anglais ou espagnol peut-être.
Moi, j'ai une question, oui. Je fais en anglais. Je ne sais pas en quelle langue, mais non, je fais en anglais. Okay, so, but it's a general question. I mean, for all these applications in the north of Quebec, where we have cold weather, the geothermal application is mainly for heating, right? So, how can you ensure a good balance between injecting and extracting heat from the soil, or I don't know, the open pit mine? If we heat all the time, we will get a colder temperature in the soil or the water. So is this a problem, or do you plan to also have some cooling, or I don't know, just want to understand about this aspect, the balance between heating and cooling. I don't know who wants to answer.
Yeah, who wants to answer this? I guess different people can have different perspective.
Yeah.
David, this touch a bit your work. Do you want to
Yes,
start?
totally. Yes. In for example, in Nunavik, yeah, there are very low ground temperature, and as you said, like there is an unbalanced heating and cooling loads. So mainly in Nunavik, we need like heating, and in my case, what I did was to, as I said, mix the alternative, like not to put all the charge imposed to the geothermal system, because yes, that would give a cooler and cooler ground temperature. So I mix it to have a simulation period of 50 years that my entering water temperature to the heat pump, it is not lower than minus 6.6, something like that. So it's size considering this, and to have a commercial heat pump in operation for 50 years. So what I did was to don't impose all the charge for the geothermal system. But it's a very like critical like issue in this place.
So basically, to deal with ground temperature imbalance, you opt for a hybrid system to decrease the charge on the ground, which allow to exploit the system for a longer time. And maybe Abra, in your case, how would you answer that question? You're looking at a system where you try to charge and discharge the ground. So how's the ground temperature evolving over time, and do you forecast some problem for borehole thermal energy storage in the north?
Yeah, so one of the issues that I was looking at specifically was trying to keep permafrost cold and keep the ground temperature at least above the area where we were storing most of the thermal energy cold, which over time, my simulations, they ran for about 3 years. We noticed that the ground was warming a bit by bit, even with the seasonal charge and the discharge, where you're injecting at first at 45 degrees Celsius and then extracting at an inlet with an assumed heat pump at -5 degrees Celsius. So my problem, or my problem that I foresee in these colder environments is that over time, eventually, you will start to see the ground warming, and the solutions that you come up with for the short term may not be the most effective in the long term. Like a 50-year project is extremely impressive, because I think it's most important to be looking ahead into the future and saying, okay, if I do this and the ground does warm, by how much can we expect the ground too warm, and what precautions do we need to take to make sure that we are still paying attention to the natural environment and trying to, you know, not affect the communities that live in these areas as well.
Yeah, and I guess long-term simulation can be quite challenging, right? As in your case, numerical simulation are super expensive, right? And then computationally intensive because of the freezing and thawing you're trying to simulate on top of the operation of borehole thermal energy storage. Yeah.
Right.
Yeah, thank you. Oui, oui, je pense qu'on a une question de Kader également.
Salut, Asma. Hello.
Oui. Oui,
Did you
hello.
listen me? Jasmine.
Oui, on entend très bien.
Thank you very much. I speak English or as you like. Thank you very much for this good presentation. We received here from Algeria, and a very nice topic. A lot of methodology. And just one question, the latest presentation with French. Quelles sont les méthodes? Méthodologie to use la méthode pour les corrections des BHT. La dernière présentation.
Oui, alors Mira, je crois que la question est pour toi.
Je peux en français, je continue en français.
Oui.
Quelles sont la méthodologie, est-ce que vous avez des méthodologies récentes pour le calcul, les corrections des BHT, bottom hole température? Vous m'avez...
Oui, alors...
merci beaucoup pour votre présentation.
Oui, alors actuellement, on est en train de voir toutes les méthodes possibles pour corriger les BHT, mais il y a plusieurs critères pour pouvoir choisir les bonnes corrections d'abord, puis ça dépend le nombre de mesures, puis aussi comment dirais-je, d'abord, il faut savoir quel genre de critères est-ce que chaque correction demande. Puis après ça, il faut savoir que les températures seront aussi comparées ici avec la présence des DST. Ces températures-là seront comparées avec les DST. Donc, lorsqu'on va tracer la courbe de gradient géothermique, on va choisir celle qui serait la mieux approchée du gradient donné par les DST. Alors, je ne sais pas si ça pourrait répondre à vos questions.
Merci beaucoup. Merci. J'ai bien reçu.
Oui, je crois que pour ces méthodes de correction-là, l'idée, c'est peut-être d'abord de regarder les solutions analytiques type Horner, mais qui sont parfois difficiles à appliquer parce qu'on a besoin de plusieurs points de température, alors que les méthodes empiriques sont peut-être plus faciles à appliquer, mais des fois sont simplistes et on doit les considérer avec un grain de sel en prenant soin de comparer avec des températures vraiment à l'équilibre, comme les températures ici de DST qui sont jugées plus près de l'équilibre, en fait, là, pour être sûr d'avoir une bonne correction.
D'accord. Merci.
Très bien. Est-ce qu'on a d'autres questions? Do we have more questions? I think there's a bit of feedback, Kader, je pense, de ton côté. Je ne sais pas si tu peux mettre le microphone en sourdine.
J'ai bien reçu tous les présentations. C'est bien. We received all presentation. It's okay.
Yeah, can you just mute, Kader? Because I think there's a feedback loop. Le son revient un peu.
Ah, d'accord. Peut-être c'est dû à la connexion. Donc, j'ai dit que c'est bien. J'ai reçu toutes les présentations. Merci beaucoup pour...
OK, très bien. Do we have more questions? Oui, je crois qu'on a une main levée. INRS, I think you can ask your question.
Yeah, good morning, good afternoon. Yeah, Georges Porries from University of North Dakota. Interesting question. Interesting presentation. Just I have about I have a question about the energy storage BTS. Have you seen or in your analysis the interbedded, that means the idea is to store in sandstone or in some geological homogeneous reservoir. But how affect, or have you seen how affect that interlayers, shell interlayers, or how affect that in the vertical permeability and or horizontal permeability? You know, how affect that not homogeneous reservoir that is typically that we are going to find in the if we want to store energy. What do you think about that?
Yeah, Abra, do you have some answer? Because I think it belongs a bit to your work.
Yeah, I'm just gonna make sure that I understand the question correctly. Are you asking what occurs in a non-homogeneous reservoir when you're
Yes.
injecting and extracting?
Yes.
To the permeability there? Okay. So my system is a closed loop system. So we're not injecting or extracting fluids directly. We're actually using ethyl alcohol as our transport fluid, and it's just a completely closed U-tube borehole heat exchanger for my project. So the permeability, we actually aren't too concerned about. The only time I would see that being affected is if the system were to actually break, which would be possible if the sediments were thick enough for the consolidation that I talked about to occur in that permafrost zone. But other than that, the permeability should remain intact actually over time for my project.
Yeah, and
Right.
in your case, Abra, we could look at it analogously, right? Instead of injecting heat and transferring heat through a fluid and having some convection movement, your heat transfer goes by conduction, right?
Mhm.
So in your model, you have different layers: the overburden, which has a lower thermal conductivity, and the bedrock, which has higher thermal conductivity, right?
Right.
So instead of permeability impact, it's more of a thermal conductivity impact.
Exactly.
So do you see maybe more heat going down into the upper part, the lower part, or does this have an impact on the heat transfer because of the thermal conductivity of the layers that are different?
Yes. So what we discovered is that thermal conductivity is a lot higher in the sedimentary layer. So over time, it's definitely possible that as we store more heat in the subsurface, which is mostly bedrock, which has a high thermal conductivity as well, the heat could propagate upward into the sedimentary layer outside of the zone in which we've air insulated the borehole, which is why my thought was, since there's only 4 meters of sediment overlaying that bedrock, it would be better to insulate with air further down into the bedrock. So that way the heat couldn't propagate all the way up to the sediments and spread much more rapidly. But it's difficult to say what the effect will be after 3 years, just because 3 years is all that we've modeled. So that's a good future area of exploration, I think, is seeing what would happen after 10 years or 20 years with that solution in place.
Yeah, so not sure if that answer your question, Eres.
Yeah, great. Thank you. Thank you.
All right. Do you have other question from the audience? No? Yes? Je sais pas, d'autres questions? I guess if there's no more question, going once, second, third, yeah, no, that's good. I guess there's no more questions, so I guess this ends our presentation. Daniela, you mentioned that, well, this was recorded and this will be posted
Sure.
on YouTube.
Yeah.
So if some people want to watch again, or if you want to share with some colleagues that could not attend but would like to have a look of our research, please feel free to distribute when this is available, and maybe just write to us if you have some questions.
Okay, sure, nice. We'll let you know once we'll be in YouTube. And no, thank you very much for your time and your work. And let's keep in touch and maybe see you you all in Portugal in October.
Yes. Geothermal field trip in Portugal will be there.
Okay, thank you very much. Bye.
Bye.
All right.
Bye.
Bye-bye,
Bye.
everyone.
Bye.
Have a nice
Bye.
day.
Have a great day.
Bye.